How could we have been so wrong for so long about quantum mechanics? All the things that we are told about quantum mechanics is wrong.
Standard quantum theory describes a wave function that evolves forward from an initial measurement. Professor Yakir Aharonov says this is wrong. Aharonov, the co-discoverer of the Aharonov-Bohm effect and a pioneer of weak measurement theory, has spent 65 years revolutionizing quantum foundations, and this is his first and only time he's given a podcast. To him, quantum reality requires two wave functions, one propagating forward from the past and another propagating backward from the future. This is ABL theory, also known as the two-state vector formalism. It explains weak measurements, which are observations that are so gentle they extract information without ever collapsing the wave function. And that's why Yakir thinks it's absurd to think that the quantum system ever collapses. Aharonov then discovered phenomena such as quantum Cheshire Cat, where a neutron's spin physically separates from the neutron itself and travels independently. He's one of the most influential living quantum physicists. This conversation was filmed directly in his home in Israel, and it captures the revolutionary thinking process from the man Heisenberg championed, whom Bohm mentored, and whose ideas Feynman called beautiful. The professor has a thick accent, and I've meticulously transcribed and verified every word, so please enable subtitles for the optimal viewing experience. So, sir, why don't you tell me a bit about how you view the world?
I told you that I am getting close to really finally understanding quantum mechanics. You know, I've been working for 65 years and struggling all the time to understand better and better quantum mechanics. While I made progress, each time I made some progress in understanding, it led to an discovery of new phenomena and new effects, and that shows that I'm in the right direction. And I think I finally arrived at a complete new interpretation of quantum mechanics. You know that when you have a theory of the world, like quantum mechanics, it's not enough to have just a good mathematical formulation. You must have also a story that you are able to tell about it that is free of mathematics. Because the mathematics cannot tell you what questions to ask it. It can answer any question you ask, but it cannot tell you what are the interesting questions to ask. In order to know what interesting questions to ask, you must have a way to understand what the theory means, not in mathematical terms, but a new kind of intuition or story you can tell about it that will be as much as possible free of mathematics. That story, if it's correct, can help you to see things in the mathematics that otherwise you wouldn't have been able to see. So that is the importance of good interpretation. So the first step is to show that the kind of story that everybody is telling about quantum mechanics is completely wrong. I will tell you the type of story that people usually tell about quantum mechanics. They say the following thing. First of all, they say that contrary to classical physics, the quantum world is not deterministic. That means that even if we know everything that we can know about a given system, like an atom, for example, we cannot predict when it will decay and emit a photon. One atom will emit the photon after 1 second, and the other atom, which is completely identical, and it has exactly the same surrounding, will emit the photon after an hour, for no reason at all. So that is the thing that made Einstein completely angry. He said, I don't believe that God plays dice. I don't believe that nature is capricious or unreasonable, because we always thought in science that everything that happens must have a reason. And here, for no reason at all, one atom behaves one way and the other another way. So people say about quantum mechanics, we simply have to accept it, that the world is non-deterministic, for no reason at all. We just have to take it as an axiom. And my first point is that it's not true. In fact, we can show that just because nature is not deterministic, it allows the system, the quantum system, to have properties that it could not have if nature was deterministic. So there is a reason for this indeterminism, as I will describe. And once you find a reason for it, then it's not anymore that nature is capricious. It does it for a given reason. So that's the first thing that is wrong, what people tell us about quantum mechanics, that for no reason at all, the world is not deterministic, there is a reason for it. The next thing we are told about quantum mechanics or quantum domain is that every measurement that we do on a quantum system necessarily disturb it so much that we cannot say that what we saw what was there before, because really most of what you see is because of the way that we disturb it. So that is completely wrong again. I have discovered a new kind of measurement that I call non-disturbing measurements or weak measurement that don't disturb the system at all and nevertheless tell us all the information that we need about the system, provided we can have many examples that we can test. So we will discuss it more carefully, but the idea is that it's not true that there is no reality in the quantum domain. There is a reality, but in order to find it, you have to do the right measurement that don't disturb this reality. Okay? That's the next thing. The last most important thing about we are told about quantum mechanics, which is wrong, is that a quantum particle, like electron, can be either a particle or a wave. They say that the electron, for example, in hydrogen atom is like a wave surrounding the proton. Not a particle rotating around the proton, but a wave surrounding. So we think about quantum particles as if they are classical light waves. But classical wave has a property that if you look at one point on the intensity of this wave, you don't change the wave at other places. But the wave of the electron has the property that if you look at one point and find the electron there, the whole wave disappears magically and is left only at the place where you found the electron. Now that is an illogical behavior, because if a moment before the charge of the electron and the mass of the electron were spread all over the wave, and then you finally find it in one place, then all this charge must have collapsed very quickly to this point. That will create a lot of radiation and disturbance that you never see. So that is not the right description. On the other hand, people say, but look, it must be a wave because there is no other way to understand why we see interference on the individual electron. For example, you take an electron and send it through a screen that has two open slits. And if only one of the slits is open and later you put a photographic plate and collect one electron after the other, you see the pattern that's called diffraction pattern. You see a spread of points of wave that came from one slit. If the other slit is open, you see the wave that came from the other slit. But if you open both slits, each electron that comes must go through both of them in order to explain that you got destructive interference, that there are points on the photographic screen that suddenly no electron appear there if the two slits are open. But if only one slit is open, any of them, it will appear there. So people say because of that, there is no way to understand that behavior, and it will say that the electron also can be a wave. And I will show again that that is not true by doing the kind of new experiment that I'm talking about, I can see the interference pattern, and nevertheless, afterward, I can do a measurement that will tell me through which slit the particle went. So you must have another explanation for interference, not by weight. And I found that interpretation. In fact, I found that interpretation of of this new behavior already in the 60s. In 1964, I came to Munich and I visited Max Planck Institute. And I was introduced to Heisenberg, who was alive then. Yes, few more years after that, he was alive. And then when I entered to his room and we were introduced, I asked Professor Heisenberg, do you know how to explain interference in your language? Because the language of Heisenberg was a language that was still used of position and momentum and the dynamics, new dynamics that correspond to matrices instead of usual variables. So there was the dynamics that's called non-commuting dynamics. So anyhow, I asked him, your dynamics, do you know how to explain the interference? He said he doesn't know. So I showed him my new way to think about it. And he got so excited. And from then on, anyone that came to visit him, I was told by his assistant, Peter Du, that the first thing he would take him to a blackboard and show him how to understand the interference in his picture. So the way that I think about interference is by showing that in quantum mechanics, there are the basic equations of motion, or Heisenberg equations of motion, are non-local. The electron, even though it moves at one point, has another variable that will tell the electron later where to appear on the photographic plate, and that variable has non-local equations of motion. So although the electron goes through one slit, that variable knows that the other slit is open or not because there are non-local equations of motion. And at first you think if there are non-local equations of motion, something terrible can happen because it will destroy causality. The particle goes through one slit, you open the other slit, and instantaneously that variable knows that the other slit is opened. So that way that quantum mechanics gets out of this problem is by having the uncertainties that if you know from the past through which field the particle goes, that variable that has the non-local equation of motion is completely uncertain. But if you use pre- and post-selection, you can prepare initially the particle that you don't know through which field it goes. You then check the interference pattern by looking on it with big measurements and do this on ensemble, so you don't disturb any of the particles. And then after you see that interference by with measurement, you can check through which field the particle went. And that will save you from causality. And you can see that the new thing about quantum mechanics is the non-locality that is allowed only because you have uncertainties. That's a very subtle point. Okay, so to summarize, all the things that we are talking about quantum mechanics is wrong. I writing now an article that I call it, how could we have been so wrong for so long about quantum mechanics? All the things that we have been telling about quantum mechanics to many the streets, look, quantum mechanics is such a mysterious theory. The particle can be at the same time at two different locations.
Right.
There is no reality there. There is no reason there because two atoms for no reason behave differently. So the world, according to this story, is so illogical that people, philosophers and writers now say that we have to look at the world as something completely uncertain, because that is what quantum mechanics tell us about. And that story is wrong. Okay? So this is my main mission, to show that the way that we have thought about quantum mechanics is really wrong, and we have to think about it in a new way. Now, once you think about it in this new way, and you learn to look at quantum systems without disturbing them, you find a beautiful new reality that can be checked only by this kind of weak measurement. And I found a host of new phenomena that is related to this reality. Perhaps the most entertaining phenomena is that I call the quantum Cheshire Cat effect. You know, the story about Alice in Wonderland that was written by
Yes.
Curt, right? And this Alice comes to this beautiful world. She can talk to animals there, and she met a cat. She talks to the cat, and after a while, the cat gets angry and disappears. But it disappears in a very strange way. First, the tail disappears, then the body disappears, then the face disappears, and only a smile is left. And Alice thinks to herself, I've many times seen a cat without a smile. But what could be a smile without a cat? Doesn't make sense. So everybody that reads this, including me, when I read it in high school, I thought that Lewis Carroll was crazy to talk about a smile without a head. But it turns out that quantum mechanics tells us that that can really happen. What I've shown is there is a very interesting effect. You take a particle like a neutron that has a property that's called the spin. The neutron can rotate around itself and produce a magnetic moment. That rotation is called the spin. And it turns out that it's possible to do an experiment where you send the electron in one side and the spin leaves the electron and moves by itself on the other side, and then they join again. So the spin is like the smile of the cat that can leave the neutron, although everybody thought the neutron can never exist without the spin, and the spin cannot exist without the neutron. This is one of the kind of new phenomena that I found once I started to think correctly by using pre and post selection. And there are many, many other effects that something we call super oscillations and quantum work that are new directions in mathematics that came out of this world. And there are many other beautiful results, especially that when you have an electron, when you do pre and post selection, you find that the electron can have together with it a pair of another electron and a counter electron that has a negative mass and the opposite charge. And if you only do with measurement, you see those new kind of entities that I call quantum counter particles. So there are beautiful new phenomena that you discover once you think properly about quantum mechanics. So the first idea is when you have two atoms that are exactly the same, but they behave later differently, you say that this later experiment tells you that in fact from the beginning the two atoms were different, but you couldn't find it in the past, you can only find it in the future. And I reformulated quantum mechanics by saying that in order to describe the present, in classical physics, to describe fully the present, it's enough to know the initial conditions in the past. In quantum mechanics, in order to describe fully the pattern in the present, you must do two experiments, one before that give you one boundary condition, the past, the wave function that you found before propagates to the present, and later you do another experiment that gets different results for one atom and the other. That different result give you another boundary condition, and that new thing that is called a wave is propagated back from the future to the present. And both information from the past and from the future, which can happen only quantum mechanically, because logically, once you know the past, there is no new information in the future. But in quantum mechanics, you have new information in the future, and both informations are relevant in the present, provided you do only with measurement to check them. Okay, that is, in a nutshell, the ideas that I want to discuss in this interview. So
That's perfect. The Economist covers math, physics, philosophy, and AI in a manner that shows how different countries perceive developments and how they impact markets. They recently published a piece on China's new neutrino detector. They cover extending life via mitochondrial transplants, creating an entirely new field of medicine. But it's also not just science. They analyze culture, they analyze finance, economics, business, international affairs across every region. I'm particularly liking their new insider feature. It was just launched this month. It gives me a front row access to The Economist's internal editorial debates, where senior editors argue through the news with world leaders and policymakers in twice weekly long format shows. Basically, an extremely high quality podcast. Whether it's scientific innovation or shifting global politics, The Economist provides comprehensive coverage beyond headlines. As a TOE listener, you get a special discount. Head over to economist.com/TOE to subscribe. That's economist.com/TOE for your discount. So I want to see if I'm understanding correctly.
okay,
Are you specifying right now the two-state vector formalism?
yes. In quantum mechanics, a pattern is described by a vector in Hilbert space. That vector in the Schrödinger representation is described by a wave. And the Heisenberg representation is described by some observable that tell you what this vector is. But anyhow, you have a vector that comes from the measurement in the past. It propagates according to the Schrödinger or Heisenberg expression of motion to the present. Then, later, you do another experiment that distinguishes between the two particles that started in the same initial condition. One of them moves to the right and the other moves to the left. If you take only those that move to the right, it gives you another boundary condition, another vector that you can send it back from the future to the present. And both vectors on equal terms tell you the full information about the present. That is called the two-vector formulation that I did discover in the early 60s. Okay, yes.
What I'm wondering, sir, and I would like to get to some historical stories with Bohm and with Heisenberg and so forth, but what I'm wondering right now is when we were speaking off air, you were referencing that you have...
Let me tell you the history. The history of how I met Bohm
Sure.
and how we did work together. I studied at the Technion in Haifa in the science faculty, and I got a course. I was taught quantum mechanics by the famous Nathan Rosen. You know, the famous article Einstein Podolsky Rosen, one of the most famous articles in history. Rosen is that Rosen, and he taught me quantum mechanics. Beautiful course. At the end of the course, each one of the students was supposed to write a final short thesis on any subject that he wants to choose in order to get the grade for the course. And we were supposed to come to Professor Rosen and tell him what we decided to work on for this grade. So I came to his office and said, Professor Rosen, I would like to work on the quantum theory of measurement. He said, no. That subject is only for very old people like me. You should do some proper physics work, like something in solid state, or something that is real down-to-earth physics, and not this philosophy about measurement theory, because old people waste their time. Nobody will understand it anyhow. But I told Professor Rosen, look, the only reason I decided to study physics is because I was interested in foundational problems. And that's why I want to work on it. He said, no, you will waste your time. So we had this impasse. And I went out to the corridor with long face, and I met an assistant by the name of Jaimungal. They told me when he heard what happened, look, there is a new professor that just arrived in the Technion by the name of David Bohm. Go to his office, maybe he will help you. So I came to his office, entered to the office and introduced myself, told him about my problem with Rosen. And he asked me, what do you want to what are you thinking about? So I told him the kind of problem that interests me. Said, okay, it interests me too. You will work with me. I will tell Rosen that you will be now my student. And that's how we started to interact together. After 1 year, he had to leave Israel. He went to England, to Bristol, and I came along with him. That's where I did my PhD. That's where I discovered the thing that's called our Bohm effect. And that was a beautiful thing that happened due to McCarthy. I think the only good thing that happened from McCarthy was the fact that Bohm had to leave United States because Princeton, that was very conservative, that Bohm is called to testify in front of the McCarthy committee, they immediately decided to fire him, not to give him tenure. And then he had to leave the United States. He went to Brazil. And then when he was in Brazil, he was called by the committee to come back and testify about the trial of Oppenheimer. And Bohm refused to do it. So they took his passport and they removed his citizenship so he couldn't come back to the United States. And that's why he decided to come to Tyson and Haifa. So that's the only good thing that happened from McCarthy. Okay, that's how I met Bohm. So that was the initial step.
Let me see if I got this timeline correct. You collaborated with Bohm to come up with the Aharonov-Bohm effect.
Yes.
Okay, that was toward the end of the 1950s. And then in the 60s, you articulated your two-state vector formalism.
Yeah, that was after I finished my PhD with Bohm at Bristol. I went for 1 year to Brandeis University as a research associate, and then I came as an assistant professor to Yeshiva University in New York. And when I was there, at that time it was a very good physics department. There was Leibovitz there, David Finch at the time, and uh, and Peter Bergman, who was the assistant of Einstein, was a visiting professor there. And while I was there, I started to think about the idea of that the future vector is also relevant. I told it to Bergman and Leibovitz, and they got excited, and that's how we wrote this article that's called now the ABL formalism. That was in 1961 or 62.
What was Bohm like personally?
Oh, he was a beautiful person, was extremely intelligent, but I think he was affected very badly by the um, by what happened to him at Princeton, and that is what caused him later to devote most of his time to work that was not really proper physics. I mean, became more and more philosophical work. But when I interacted with him, he was still really extremely brilliant. In fact, Einstein told that he looked at Bohm as his real follower of his, and Feynman, when we wrote the article of the AB, Feynman sent us back a cable saying how beautiful, how come I have not thought about it myself? So, and Feynman said also about Bohm that he was the only one that he knows that was smarter than him. So Bohm was really extremely smart, but very kind person, and it was a really beautiful experience to work with him.
That's rare of Feynman to admit.
Feynman told it to someone, I don't remember to whom, that the only person that he met that was smarter than him was Bohm.
Tell me about what line of thinking led to the Aharonov-Bohm effect.
What led us to the work? What led us to the idea?
Yes, that you can shift the electron's quantum phase, and so you can have
Yeah.
global gauge features, but not
Right.
just local forces. And those local gauge features must be taken as physically real.
I can tell you how I came to think about this idea that led to the Aharonov-Bohm effect. I was excited as a graduate student when I learned about laws that showed that if you have a periodic potential in space, like in crystal, then you have something that is very interesting, that you develop a gap in energy because the periodic potential makes a particle with positive momentum jumps to negative momentum, and the superposition gives you a gap in energy. So when I thought about it, I thought, why don't I try to do the same thing, not in space but in time? I will take a periodic potential in time, and maybe then I will get a gap in momentum, because if I change position to time, I have to change energy to momentum. And luckily, I didn't know anything about gauge transformation. I was ignorant. If I knew about gauge transformation, I would know that periodic potential in time cannot do anything. But I did not know about it, so I started to calculate, and I saw, to my dismay, that the only thing that happens when you put a periodic function of time is that you change the phase of the wave function. That does not lead to any observable effect. But then it occurred to me that if I will put one potential in one place and a different potential, time-dependent potential in another place, then I will get a different phase. And that different phase can be observed. So I thought about an idea that I have two Faraday cages, and the electron can be either in one of them or in the other. When it's inside the Faraday cage, it's completely protected against any electric fields outside, because it cannot penetrate the Faraday cage. The only thing that can penetrate is time-dependent potential. So I have different time-dependent potential in one Faraday cage and another in the other Faraday cage that will produce a different phase, and then I can open the Faraday cages after I remove the electric field outside. The electron will go out and interfere, and that interference will show that there was an electric field between the two Faraday cages, and the electron did not touch that electric field, but it still felt it. So that was the beginning. I came to Bohm and told him about this idea, and he said, that's very interesting, and he came out with the modification instead of the Faraday cage. The thing that appears in our article is two long cylinders, conducting cylinders. But let's say for a while, we haven't published it yet. And then I went to a summer school at Oxford, where they talked a lot about, at that time, the thing of the structural level thing in physics was a terrible time when you had infinities of the electromagnetic field. People did not know what to do it. So Heisenberg suggested that instead we have to talk only about scattering or asymmetries. And then there was a whole mathematics around it called dispersion relation. And the whole physics at that time was horrible, just lots of mathematics. But anyhow, I wanted to find out what it's all about. And when I was there at Oxford, they discussed also the effect not only of stellar potential, but also of vector potential. And then it occurred to me that maybe we can generalize the thing that I talked about the 2000 cases for the case where I have a magnetic field in the middle and different vector potential on both sides. I came and told that about to Bohm, and then he really got excited. And he said, okay, if you are able to solve the problem of infinite line of flux and see what happens to electron in that phase, we'll publish the article. And that was the way that it came about. And I remember that at that time, there was, in England, there was the fashion to have tea at 4 o'clock in the afternoon, where graduate students and professors at Bristol were sitting together. And I told everybody about this idea. I said nobody could do the experiment because the electron has such a small wavelength that if it has to go around a solenoid, a macroscopic solenoid, there will be no stable way to see the interference. And there was a professor there by the name of Sir Frank, who said, wait, I know what you can do. If you have a thing that's called magnetic whisker, that's like a small thin magnetic flux that goes inside the crystal, you can do the experiment around this magnetic whisker. And Chambers, who was a professor, experimental professor, that sat in this meeting, said, I'm going to do this experiment. And that was the beginning of the experimental work from the Aharonov Bohm. Now, it's very interesting that when we published the article, and Price, who was the chairman of the physics department at Bristol, went to visit Max Planck Niels Bohr Institute, and he came back and said that Niels Bohr doesn't believe that the effect is correct. In fact, many people could not believe that the effect is right, but later the son of Niels Bohr finally convinced him that the effect is correct. And of course, even today, there are still some people that think that something is wrong with the effect because it looks very strange that the particle can feel the potentials and all the force, but that's certainly a true quantum effect. That was the first occasion where I realized that the basic equations in quantum mechanics must be non-local, the Heisenberg equation, because the force affects non-locally the particle that is at the distance away. So that was the beginning of my thinking about non-locality in quantum mechanics.
Can you explain how you see what gauge theory is to people who aren't physicists, but also just keep in mind that many physicists watch this program, professors of physics, researchers, postdocs, and so forth.
Yeah,
So you can also explain to them how you see gauge theory.
First of all the interactions that we know in nature, the electromagnetic interaction, the storm interaction, and the wave interaction, and the gravitation, all of them are described by potentials. Now, but that potential, because the locally they are not observed, they must have some freedom that you can change them without changing the physics. Now, why do you need potentials? It turns out that if you, in classical physics, it was known that you can formulate it in two ways. Either you use the Newton equations of motion, which just uses forces, then came Hamilton and showed that you can also write classical physics by using Hamiltonians and using the Hamilton equation of motion, and for that you need potential. So in order to be able to describe forces in the canonical language by using Hamiltonian, you must have potentials. But the potentials have the property that they have a freedom. You can change the potential but without changing the forces. That freedom is called gauge transformation. But the potentials are necessary if you want to formulate even classically Newton's equation of motion by using not Lagrangian but Hamiltonian, you must use potential.
Why is it that you're saying that the Aharonov-Bohm effect indicates that reality or nature is non-local?
Because I believe that the fact that you write a local equation by using potential, that is misleading, because suppose I say the electron moves only on one side, and there is a vector potential there, and it's affected by this vector potential. But I can use gauge transformation that will completely make this vector potential on one side zero, and nevertheless, the electron still affects the force. So the fact that we can use it like a local equation is misleading, because we can always move by gauge transformation, remove the potential from the region where the party is moving, and the party still feels the effects of the force, finally. So there is no way to describe really the effects of the force locally. It's a mathematical formulation that uses waves, but both the waves are not real and the potentials are not real. The only thing that you can really observe are the forces. And the idea that we describe the electron by wave, as I have shown, is misleading. You have to describe it by a particle that moves only on one side, but it feels non-local with the force.
You just mentioned that the waves are not real and the potential is not real. So in your mind, what is real? What is ontologically there in physical reality?
I think that if you think about the way that that quantum mechanics started, there was first the Heisenberg approach before Schrödinger, and Heisenberg described physics still by using position and momentum as the fundamental concepts, but he said that instead of using the position momentum as uh, numbers, I have to use them as matrices. And he wrote the equations of motion for these matrices. But it turned out that it was very complicated to solve the Heisenberg equations of motion. People could do it for harmonic oscillator and for hydrogen, but the minute they tried to solve the Heisenberg equation of motion for something more complicated, like an atom with two electrons or any other non-harmonic oscillator, they could not do it. Then came Schrödinger, following the Boyle idea that electrons could also be waves, and wrote a very simple wave equation describing the electron, and that wave equation, it's called the Schrödinger equation, was extremely simple to solve. And then there you could very quickly solve much more complicated problems. And then all people left Heisenberg and went to Schrödinger equations and say that is the right physics. And poor Heisenberg was claiming all the time that could not be true. That is not what quantum mechanics is about, but nobody listened to him. People say that, no, an electron must be waved, we see interference, we have the Schrödinger picture that's so nice. And I think now that the Schrödinger picture is only a mathematical way to solve the Heisenberg equations of motion. You solve what happened to the quantum vector, the Schrödinger representation, but to me, the wave is like potential. It's like a mathematical aid to solve the problem, but it does not show what is really there. And what is really there are observables that are function of position momentum, and you can follow what happened to those observables if you know how to solve the Heisenberg equations of motion. So the particle, even quantum mechanically, the particle still has to be described by a point. You don't know where it is at any given time. It moves very disorderly, but you can find a way to see the property of what happened when you pre and postulate. Then you can see indirectly what is called the wave. If you have many particles that are described by the same state, then you can actually observe on the average of these particles the wave. But the wave is only an average property of many particles, not of each individual one.
Did you ever try to make a gravitational version of the Aharonov-Bohm effect?
Yes, definitely. With my first PhD student, we wrote analog of the AB effect, both for Young-Mills theory, non-Abelian gases, and for gravitational theory. But later people made a lot of other modifications. By the way, there is a very interesting historical story, apart from the one I told you, that Young, the one that got the Nobel Prize together with Lee and Young, he did work on the Aharonov-Bohm effect, and he showed, explained by using the AB effect to explain why flux inside superconductor must be quantized. But each time we refer to Aharonov-Bohm effect, he called it the Bohm-Aharonov effect. So one time I met him in Japan, I came to a conference there, I asked him, why do you call it the Bohm-Aharonov effect? He said, oh, of course, because he was your thesis advisor, must have been his idea. I said, no, it was my idea. So he said, look, if you want me to refer to it differently, ask David Bohm to write me a letter in which he will state that it was actually your idea.
Interesting.
So I went to David Bohm, told him what happened, and he wrote a letter to Young. And then Young sent me a letter saying, okay, from now on, I will start to call it the Aharonov-Bohm effect, because that's what Bohm testified in his letter. I have this letter from Young. Yeah, he wrote a letter to C.N. Young, stating that in fact, the first idea of the AB effect was mine, and he only helped me later to perform it better. And then from then on, Young started to call it the Bohm-Aharonov effect.
You mean he then started to call it the Aharonov-Bohm effect?
Aharonov-Bohm effect.
Right.
And he sent me a letter saying that indeed Bohm confirmed that it was my idea.
At this point, we were having so many internet connection issues that we decided it was better to stop here, especially since Yakir wants to hear from you, answer your questions. So this is part 1. Part 2 will be coming out in a few weeks. Leave any questions in the comments section below. And of course, subscribe to get notified.